Good morning to all of you. So
Good morning, sir.
Yeah, good morning. So welcome to Thermodynamics lesson after little long time. Sorry about this missing of many classes because of the exams usually held on Fridays. So today, luckily, I didn't have any exam duties, but somehow we will reschedule the missing classes so that we can understand the subject thoroughly. That is very important. Today happened to be the lesson 4 and 28 January 2022, 4-hour session. So we will see how we can manage learning this subject. That is very important, learning and understanding, because thermodynamics is not for the memory. So today it's a different approach for you to explain this subject, to understand this thermodynamics, some very important things. Okay, so learning thermodynamics from the balloon. Okay, so I purposely put this because I thought of how to explain some thermodynamics phenomena in the simplest ways. Otherwise, you will memorize it. Memory doesn't work in thermodynamics. And to feel the thermodynamics, we have to understand it. It is wonderful. That's why I thought of today, because you all have experience. Even sometimes the blowing competitions also you have attended in your childhood time. So everyone knows about this. So that's why I thought of learning out of this today, to learn some very special concepts in thermodynamics and see how we are evolving from balloon to technology masterpieces afterward. Yeah. So I hope you all can feel mentally. Yeah, you're blowing the balloons even childhood. So do you agree with this? The balloon. Imagine the environment of the balloon. Imagine the environment of the balloon that is surrounding the balloon. You can understand the balloon environment. And so when the balloon blows, okay, the internal volume becomes more and more. And it is taking the environment or the surrounding. Okay, environment or the surrounding. So now we can say that when you blow the balloon, it takes the space in the surrounding, means you are displacing the environment. The balloon is displacing the environment. Okay. So the balloon is displacing the environment. Okay. Understand? Can you imagine? Can you imagine? So if you think of this displacing the environment, towards this direction, it is something like positive displacement, displacing the environment. This is something like positive for the balloon because balloon is getting bigger and bigger. Okay. And the reverse, if releasing the air inside, so it is something like a negative, but anyway, it's a kind of displacing the environment again. Okay, very interesting. Yeah, understand? Yes, I believe you can understand. Thermodynamics material easy. Is it so easy? Then, actually, what here blowing means, you make the flow of air. Okay, you make a flow of air. Okay, you are creating a flow of air. That is from the mouth. Okay, you are creating a flow of air. Sure, make a flow of air, and that air goes into the balloon. Air flows into the balloon. Flow of air into the balloon. Interesting. Make a flow of air into the balloon. Okay. Obvious. And who makes this? You make this. Okay. So this flow coming out from the mouth, flow into the balloon, and then the balloon becomes enlarged and it's displacing the environment. So two things. So there is a flow of air, you make it. So there is a flow work. Flow work, because you are doing a work, you are putting an effort. You fail it. And even for you, there is a limitation. There is a limit for you. There is a capacity, physical capacity for you to blow it. Okay, not to the fullest. If not, you have to use an air pump. Okay, then you can make it more. Even air pump, there is a flow work. So here, there is a flow work done by you. On the air. Okay. So two things here. Flow work. And there is a flow. Okay. There is a flow. Interesting. To make a flow possible, okay, there should be a work done on the flow. Okay. To make a flow possible, there is a work interaction. Here we call it flow work. Let's say this is for a flow. Yes, this is good. Okay. I will take a simple example, more familiar to you. Today lesson is quite challenging, so you should listen very well. Yeah? Let's say I take a block of mass. Let's say this is something like a block of wood or steel or whatever, a block of mass. And you know the Newton's second laws. So if there is a force, let's say this is the net force applied. That's, of course, when there is a force applied, of course, the momentum change, and we can see with the continuous application of the force, this mass moves. Okay. Continuous application of the force, this mass moves. So same way, let's say, yeah, so I put the middle as well. Let's say this is the resultant force. Yeah. So if because of the flow, because of the force, there is a displacement of this block displaced. Okay, go to here, you can see the displacement. So this displacement, if this displacement, let's say d, because this force is needed for this. So there is a work done. Okay, there is a work done to make this mass move. There is a work done. We call this force times displacement. Okay, force times displacement. You know this simple expression. Okay, work done is force times displacement. Now let's say in a pipe flow, let's say this is a pipe. Let's say this is a pipe. This is a pipe. And a flow means same like this. So let the pipe a little. It's same like this. So you can see packets of, let's say this is water, something like packets. Okay, your segments are moving. You can imagine like that. Okay, you can imagine like that. You can imagine like that. So perhaps initially one packet is here. Initially one packet is here. Let's say I mark this with some special color. So after a while, this moves here, moves here. See? So there should be a force on this block. Net force. If not, this won't move. Okay. There should be a continuation. Okay, there should be a continuation. This is for you to imagine. This is for you to imagine and understand and not to memorize. There should be a continuous force. Good. So that's why there is a flow work there, even in pipe flows, maybe water flows. Air flow also the same. Okay. So in short, flow. This could be the flow of liquid or gas or even vapor or even liquid plus vapor, whatever. So flow work is relevant when there is a flow. So flow work is relevant. Okay, flow work is relevant. You no need to think that much, but simply try to have some little understanding. So we're done. So in simple terms, for a flow, we call it flow work. So blowing a balloon, also something like a flow work. Okay, you add some work on this flow. Also, you are creating the flow. There is a flow work. Addition of work onto the flow so that the flow makes possible. Okay, flow work. Interesting. Okay, very interesting. And in the flow works, there is a displacing effect on environment or surrounding. So this balloon example is very nice. Okay. This balloon example is very nice. When you do this flow work, you feel pressure. And the balloon is expanding, so there is a volume as well. So the balloon pressure is same as the pressure you have to blow from the mouth. And this all the volume came out from the mouth. So if you think of flow work, interesting, eh? Flow work. One-time learning. Okay. Flow work. You feel that without this flow work, it is not possible to blow the balloon and not possible for the air to have this effect without flow. So this makes sense. So we should be able to evaluate this flow work. Okay. Before evaluating, we should be able to, okay. Before evaluating, we should be able to understand the flow work. Flow work. You never thought. Because of this flow work, this blowing of balloon become possible. Okay. Blowing of this balloon is possible. And the next, I will do this way. So if there is a hole in the balloon, let's say if there is a pinhole means a small hole. So when you blow, this may not burst maybe, but there may be a limitation of this. If there is a pinhole in the balloon. So it is something like this. So if a little child blow this, if there is a pinhole, cannot blow full maybe. Not possible to blow full. Because there is a little hole. So sure, no exploding. That's a little hole. For the clarity, I will make it a little big. Eh? Yes, good. What happens? There is a flow out. See, flow out. So cannot blow anymore, only little. But continuously blow. So there is a flow in as well. There is a flow in as well. Let me try to explain this. Yes. There is a flow in. There is a flow out. Yes. There is a flow in. There is a flow out. What is this? Yes, it displaced. But if there is a pinhole, now this becomes open system. And flow work continues because there is an in and out. Otherwise, there is a limitation. This becomes open system. So there is flow in, there is flow out, and flow work continues. Okay, good. Yes. So flow in, flow out, flow work continues. And there is no change in the volume. Let's see, let's imagine there is no change. There is a flow work continues. The same way, see, flow work. So flow in, flow out. So there is a flow work. Okay. I hope you can understand. A little more to do here. Displacing its environment. I take a new slide. A copy of this. So what happens when the flow out? Interesting. Yes. The flow out expands. Again, displacing environment. Okay. Because this is the flow out. It won't be something like an arrow, because inside the little high pressure, so this displaces environment again. Okay. Don't get confused. Displace it. That's true. Now I take this out and move inside, flow inside. Then that displace this. Interesting. Imagine the air inside. Oh, is here. Yes. Finally displaced. This is what takes place. Okay. This air comes from the mouth. Yes. There is an inlet, there is an outlet. Okay. In and out. So you can see this balloon is something like a system. Okay. Like open system, you can see in and out. Interesting. And you can feel the flow work. So you force in, there is a flow working. And even here, some environment is displaced. So flow work done here as well. And there is a flow work done here. So see, this displays this. This displays this. This displays this. And likewise, continuous displacement. Okay. You can see continuous displacement. Even in the pipe, that's a pipe. This one. Sorry. Yeah, good. This is a pipe. Flow. You can see. This flow also something like displace. This push this, and likewise. So there is a flow work. When there is a flow work is a kind of phenomenon. Even for this balloon, even no hole, there is a flow work because balloon stretches. So until certain limit, there is a flow work. So from where the flow work comes? Yes, from the pressure, and there is a blue. Okay, good. Interesting. This is a schematic of a steam power plant. I got this from the internet, this one. This is a schematic. So the high pressure steam comes here. Okay. And then pass through this turbine. So when it passes through the turbine, expands, and the low pressure steam comes down. So steam blow in and from here out. Okay, try to understand. This is not a very good schematic. Later I will share a better one. So you can see the same way. This effect is here at the turbine. Okay. Here at the turbine. That is obvious. In, out, but this schematic is little confusing, but you can see in, out. So from where the steam comes? From here, the flash chamber or the separator here, steam comes. So this is like you are blowing the barrel, steam comes in, and steam expands. When it expands, it does work. Later I will explain it. And then goes out. See, in and out. successive in and out. So here what's happened is, same way, the expansion takes place here. Then you can see the expansion takes place. Not very good. Comes here. Expands. Expands. And then so leaving of this. Okay. In and out. So you can see some big expansions. Actually, this schematic is not very good. So you can see expansions. Finally comes out. So comes in, is highly energized, like blowing here. Goes out, is less energized. That's the point. Okay. Highly energized to less energized. Once leave it. So here you can see highly energized. Because of the flow work. Here, for this case. In is highly energized. Interesting. Here leaving. Is less energized. Possibly less energized. Less energized. Possibly. So, less energized. Put a question mark here at the moment. And later in the applications, you will see this is less energized. So this is how is it. And now the balloon, we can say there is a volume and flow in and out. And the flow in and out, and there is a flow work in, and there is a flow work out. The leaving air here from the balloon does a work on the surrounding, because this displays the surrounding. And here this displays this air here. Push, 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 and all the while here it displays the surrounding. And also this maintains this. Okay. So that's how it is. So
Excuse me, sir.
yeah, Buddha.
Sir, when the person is flowing in,
Yeah.
he's taking air out from the space. Is it?
Yes, yes.
Should we care?
Yes, but here we are considering only the balloon in and out.
Okay.
Buddha. Yeah.
Okay. Sir. Okay.
Okay, very good. You are thinking now. Excellent. Yeah. So now let's say see, even in a balloon now, there are many things to look at. The flow work in. For the moment, flow work takes place here. Okay. Takes place there. And it depends on the P and V related to the flow in here. P and V here. In, okay, P and V. So this in, let's say this is 1 or in here. So flow work in is the pressure here. So it depends on the pressure in and the blow volume. Let's see. Pressure in and blow volume in. Yeah, because you feel the pressure and you know that there is a flow of air goes in from your mouth, leaving the mouth and go into the belly. So you feel burn. And the flow work into this balloon system depends on this. So we call function of pressure and the volume in means leaving the mouth actually is what goes into the belly. So this is just before entering, just at the entrance at the balloon. And actually this is equal to, later I will explain, pressure times the volume in. Pressure times the volume in multiplied by multiplication of this two. is the flow work in. Same way flow work out. Let me rearrange this. Flow work out. This is out, just at the leaving point. So flow work out is the P out times V out. Not times the function of P out and V out. Okay. And at any place, let's say somewhere here, because here also there is a flow work. So in general, so if you think of at that point here, a pressure P and certain volume V, then the flow work related to this V and P is P and V. Multiplication. You can imagine. Not to say, you can imagine the existence of PV. There is also continuous moving towards, because in and out continuous flow work. So here, it's a better example. See, this is a boiler here. And the high pressure steam, like blowing here on the turbine, blow in. That's why it's interesting. Same line. And see, blow. Same like a bell. Out. Less energized. Because this steam turns the turbine. So this blows in here and wind expands. This does the work as well. It's a different story, but you can see there is a leaving of this. There is a leaving of this. So unlike the balloon, this steam does a work here. Later I will explain this. Later I will explain this with a simple example. So again, you can see Here it is very interesting. At least this has the turbine effect. See, it takes the shape. That is what. See. So that's how it is. So here, you can see some similarities. Okay. But the only point is here, with this expansion, see, because of the shape, seem like the balloon anyway, in and out. This is highly energized. So when this expands, this can turn this turbine. The flow work, okay, the flow can turn the turbine as well. It is something like this, okay. It I will show you very nice example. No difference. So you are displacing. The flow comes here from the mouth, expands. And with this expansion, there is a possibility of doing a work, turning this little fan, toy fan. Okay? That's a possibility. So in and out, you can imagine. Okay? So it is very interesting. the same turbine is in. High pressure steam in and then the leaving and expansion. Okay. So you can see the fan blades. So when this steam comes and expands all the way, it is like blowing a fan, you know, blowing this little boy blowing a fan. The same way you can see. But the only thing is, here there is a more effectiveness. You can see the conical shape. Okay. And there are so many fan blades, all radially placed. So boy cannot blow this, but steam, energized steam can blow this in and out. Okay. So all the lessons are here to explain you the flow work. Okay. Flow work. And let me bring the flow work expressions from here. Flow work in and out. Flow work in is P in. P in. Flow work out is P out. Too early to send the attendance, Vitala. Okay. You listen this very well. It's P out, V out. Okay. So in the turbines, all. So this relevance is flow for the flow. Flow means in and out. In and out. So let me mark in and out as well. Put as inlet and outlet. Inlet. This is outlet. So this displaced here, and this displays the surrounding. So you can see P out, P out. So generally flow work means function of PV is P times V. I can explain this, but I will explain this afterward, not now, because your focus distracts. Yes, function of P. See how nice. Okay. And the point is, now I will take this and I will add so inlet 1, the steam comes. Of course, flow work is necessary, but what's important is the energy of this flowing fluid, energy. energy here. Okay. And the total energy here leaving. Sense? Leaving here. So energy is important. So here energy is it is too early for the attendance for that. Even I have to watch the, because once I see the chat, I'm thinking a message, but it's an attendance. Okay. Energy. Of the flow in. Okay, that's about energy of the flow in. You know, yeah, let's say this is E in. So energy of the flow in is, of course, because of the highly energized, the high temperature. Okay, because of the temperature, there is an energy we call the internal energy. We call the U. It is related to the kinetics, the violent molecular motion because of this receiving of thermal energy from this burning of fuel. So highly energized, that energy is here. Plus, there is a flow in. So there's a flow in. So this flow work we have to add, because flow work is, so I will put as this flow. So the total energy, U, internal energy, nothing to do with flow work, but flow work plus internal energy together is the total energy. So the in is U plus flow work. Means the steam, the total energy level, there is a rise. Okay, so this is how we take it. So flow work is one way. PV. E in. Okay. It's U plus PV in, and this U plus PV there is a single notation we call H with the big U here, big U. So this U plus PV together is the energy in flowing fluid, gas, water, or two-phase, whatever. The same way, out. out. E out. Let's say EO. I just put O as outlet. UO. EO. P plus PVO. HO. Okay. So energy out. We have to add this flow work as well. So other than the internal energy because of the flow, there is an energy related to this. So we call total as U plus PVO. Okay. So this is the energy in thermodynamics related energy that can be utilized in generating power when the steam passes through the turbine. Okay. This is the thermodynamics related energy. Thermodynamics related energy all together becomes H. This is for the flow, continuous, displacing and then leaving. Okay. So I believe you can understand this. Good. And I'm going to share a slide from the NASA website. Okay. Yeah. Enthalpy. Okay. So enthalpy defines a new state variable. So enthalpy is a definition. Okay. It's a definition. Enthalpy defines a new state variable that is a combination of other state variables. So these are the variables. So let's say here, I need to pay your attention on some limited variables here. Enthalpy H is defined as the sum, C plus C, sum of E. What is E? Internal energy plus pressure times volume, PE plus PV. So here in the website, it's not going to explain this, okay? But E plus PV, now you have an idea how this E plus PV came. So it is very important because this is for the propulsions, jet propulsions and all. Enthalpy is very important. Okay, enthalpy. So especially you can see the enthalpy. Okay. So enthalpy is defined as E plus PV. So that is what I need to pay your attention to. Okay. Then enthalpy. So I put here little wordings. See whether this can this makes sense for you or not. Enthalpy is a measure of heat in the system. Some says like that. Okay. Some says like that. Heat is a measure of heat. So I would say instead of heat, this is the total of the thermodynamics related energy in the system. Okay. Yeah, that is heat. They use the formula H is U plus PV. H is the enthalpy value. U is the internal energy. P and V are pressure and volume of the system. Okay. So for you, if someone knows what is enthalpy, yeah, it is defined as U plus PV. As a definition, we know this. But behind this, the physicality, you have some sense. You got it from this balloon example. Okay. Displacing flow, make the flow possible. There is an additional energy flow with this U, internal energy. Because internal energy alone cannot do this without P and V. Okay. There should be a V effect. Okay. This is for flowing fluids. Okay. The relevancy means the practicality. Means open system. There should be in and out. Further, enthalpy, because these are the ways the people are seeing this. Okay. So you try to understand this, try to visualize, try to imagine this in a better way. So enthalpy is the measurement of energy in a thermodynamic system. So this is thermodynamics energy. The quantity of enthalpy equals to the total content of heat system, because the flow work is an added energy. So the flow work becomes energy. It is thermodynamic energy, means it's a kind of heat afterward. You can consider in that way. Okay. So total content. This is flow. The flowing systems, equivalent to the system's internal energy plus the product of volume and pressure, which is U plus P. Again, the heat absorbed or released is equal to the enthalpy change. Yes, true. But this is for the flowing systems. Just try to make some sense on it. Yeah? So enthalpy says, enthalpy is a property of a thermodynamic system. True. Later we are going to look into this again. This is a property. It is defined as the sum of the system's internal energy, U, and the product of its pressure and volume, so that H is U plus PV. The pressure volume term P times V expresses the work required to establish the system's physical dimensions, to make room for it by displacing the environment. So the way that they are trying to project some better understanding by displacing, you have some understanding, and then establish the system's physical dimension. Example, the balloon shape. So that effect, the P times V is the effect of physical dimension. So it needs some work done. That is the flow work. Okay, I just put as flow work. Required to establish the system physical dynamic. Balloon is the best example. If no flow works, no balloon possible to blow. I think this one, I skip this one. I don't look into the pictures here later. I will explain this further. We come to this later. These things we will come to later. We will come to later for this. So I will add this to your daily notes. And now we have to go for your lesson 3. Lesson 3. I will take, because those days we talk about the enthalpy and H value. H. Now you know what H means. You have some little sense. U, internal energy. I think you know about internal energy. That is the energy internal, means the molecular level energy, the total. That is because of the molecular motions. That is because of the temperatures. Okay. So I'm going to do a little calculation. I'll take this slide maybe. Another slide. Won't see. So we have shared this knowledge with you. So I believe you follow the notes and all. You have a better understanding. That's why we are trying this. So let's see here. So P1 bar. So you have this. So per kg. Or, so now I'm going to do a calculation. For the selected pressure at 1 bar. Okay. And this all will help for you to understand your one-time note. Okay. So you have a task, additional task other than listening to this. You have to understand one-time note. And this helps for you to have your own way of understanding. Because understanding is different from one to another. So today we have 81 students. So 81 different levels of understanding that even no one knows. Even you have no idea what level of understanding you have, but you have an understanding. Okay. And you know that. So 81 students, different understandings. Okay. So try to have something more effective one. So my understanding also different. That's how it is. But when it comes to practical applications, all the understanding should work. The better understand, better creative, more innovative. Yes. Produce better results. Okay. That's how it is. So I'm taking here Hg. Hg. So this table, saturated water and steam. So saturated condition. You know this, I have explained this. Saturated conditions. It is very important for you to understand or make sense of what saturated condition is. Okay. In this saturated, if I take Hg, the value here shown as 2675. So this is for the vapor form in this water steam saturation, the steam form.
Sir, excuse me, sir.
Yeah, Buddha.
Sir, slide එක share වෙලා නැහැ sir. එකම slide එක තියෙන්නේ change නැහැ නේ sir.
නැද්ද පුතා? Sorry. දැන් හරිද? Is it okay?
Okay sir. Now okay sir.
කලින් තිබ්බ slide එක මොකක්ද පුතා? Which one earlier? Okay.
First මේ sir මේ content එක තිබ්බේ sir.
Right. Okay. Sorry පුතා. Okay. So here, so we take this from your lesson 3. So we are going to look into how this Hg came here. H. Okay. H. And there is a Ug value. Ug value. You can see, I'm not putting the units here. Ug value is 2506. 2506. See all the energy units, Hg, kilojoule per kilogram, kilojoule per kilogram. And I will take PV values. P is 1 bar. Okay. P is 1 bar means, put this as 1 bar. And Vg value, there is 1.694 meter cube per kg. And the Ug value is kilojoule per kilogram. Hg value also kilojoule per kilogram. Okay. So here all kilojoules. So pressure, I take the pressure 1 bar now. Because in your little smart device maybe, can you see this? Any other? Make it a little bigger maybe. No, wait. Okay, because it is this red dashed box inside, you can see the values. So P is 1 bar. 1 bar means, I think you know about the units. Bar means 10 to the power 5. 10,000. 10,000. 10,000. 10 to the power 5. $100,000. Pascal, we call Pascal. Pascal means Newton per meter square. Pascal, you know this. So Pascal is the SI unit. So since all kilojoule, kilo, so I'm taking this as kilopascals now. So 100 kilopascals. So 1 bar is to match with this kilojoules and kilojoules, I take this as kilopascals. Okay. Now this units, you have to have some understanding. Kilopascal. So 1 bar become 100 kilopascal. Now, with this, I will take PV, small v, because this also 1 kilogram. 1 kilogram. So PV, 1 kilogram of G means the steam, saturated condition. You should understand all what saturated means and all. Means don't be limited to the word. So what the word sends for you is very important. So I will take P times V. 100 times V. What is V? V is Vg. Okay. For gas phase, I'm taking P times Vg equals this. Subscript. Meter square. Superscript. Okay. So Vg. But I hope you have no issues of, because it takes time if I need to put the subscripts and superscripts. Okay. P times Vg. Vg is here. So 100 kilopascal times 1.694 meter cube per kilogram. So this one, the total becomes 169.4. Total becomes 169.4. Good. So PV is 169.4. And if you look into the units here, kilopascal times meter cube per kg. So this unit will be, see kg here, Pascal times meter cube becomes kilojoule. You check it, okay? Kilogram. The reason is Pascal times. Kilopascal times meter cube is kilojoule. Pascal times meter cube is joule. Check it. That's why you have some work as well to do. Issues. think yourself, or you can check with whatever the sources, even you can check with me. And now I'm going to do this calculation. UG plus PV. UG plus PV. UG. Now see this value. UG is 2506 kilojoule per kilogram. Plus PV is 169.4 kilojoule per kilogram. So what became the total? Because the same unit, kilojoule per kilogram. You can add apple to apple, orange to orange, tables to tables, people to people, and here kilojoule per kilogram and kilojoule per kilogram. Same unit should be. Okay. So 2506 plus 169.4. Okay. 2506 plus 169.4. So two six seven 5.4 the total. So what is Hg? Hg is 267. So this is same as Hg. Because here Hg has 0 decimals, no decimals. So 2675.4 is 2675 to the nearest whole number, 2675 kilojoule per kilogram. That is Hg. Understand? So what this says, so U plus PV is H. So here Vg here, U plus PV is PVG. So H is U plus P. And if you are going back to the previous, In a second. So this one, I added somewhere here. So H becomes U plus P based on this calculation. So enthalpy. So this is a good slide, it seems. So now you can see enthalpy is a property of a thermodynamic system. It's a property, even it's in the property table. Okay. And U is a property, P is a property, V is a property, so that U plus PV is a property. Okay. So small u means for 1 kilogram, small v means for 1 kilogram. It is defined as the sum of the system's internal energy and the products of its pressure and volume. Pressure volume term expresses the work required to establish the system's physical dimensions. Try to relate that to make room for it by displacing its environment. Okay. So I take this slide only. Okay. From this, okay, I take this slide only for your addition into today's notes about enthalpy. Good. So this is the enthalpy definitions. Definition. So defined. Define. It's a definition. Also, I will add that. NASA slide as well. Interesting. Okay. Interesting. Good. So you learned something, and shall we take a break? Now 10:22. පුතාලා break එකක් ගමුද විනාඩි 10ක වගේ?
Okay, sir.
Okay, sir.
එහෙනම් අපි 10 හමාරට එමු. මම මේකේ රෙකෝඩ් එක පෝස් කරනවා. මට මතක් කරන්න රෙකෝඩ් එක ඔන් කරන්න. මේකට අපි 10 මාට පටන් ගත්තා. හරිද? Okay. So see you all at 10:30. You have 7 minutes. Okay, පුතා. Yeah, Buddha, we are back. The record is on. Naturally, a solid, liquid, gas all form out of atoms and molecules. So this solid, you can see always in continuous vibrations. You can send the attendance later. So when it comes to liquid, move fast. When it comes to gas, much more fast. And this is just an animation. Please don't send the attendance because I'm misleading. If there are chats, the real useful ones, I may be missing because I'm not going to see your attendance anymore. It's really disturbs you, no? So at the end of the session, you can send the attendance afterward, not now. So this is the nature, and this is just for our little imaginations only. Okay. So solidity, the liquid, the flowability, and the gas has some expansion, contraction nature is there, but all the molecules are in motion. Right. This one, the average speed slowed down here 2 trillion fold from room temperature. This is for helium atoms. Okay. So the real speed is 2 trillion times the speed you are seeing here. That's how the fast, the speed of the helium atoms. Then same, the other atoms are also quite violent. Okay. And this violence, yeah, this is what resembles the internal energy. So see, the temperature of an ideal single atomic gas is proportional to the average kinetic energy. So this kinetic energy, we call this internal energy. This average kinetic energy of its atoms, kinetic energy is this, but further looking into this internal energy is 3/2 times RT. Let's say anyway, it's a function of T. Okay. So that's why always temperature. Yeah, you no need to look into further details on this, but these expressions are here for us to understand that internal energy is a function of temperature. And of course, are the specific gas constants. So later we will look into this, and this has a relationship with the molecular masses as well. Anyway, temperature matters for internal energy. High temperatures, high internal energy. The enthalpy definition is here. You know that in the enthalpy, the internal energy, these are the sayings about internal energy. The internal energy of a system can be understood by examining the simple possible system and ideal gas. Ideal gas is something like this. Single atom particles bouncing each other with no losing of its kinetic energies. Okay. So later we will learn about this. So the internal energy of an ideal gas, let's say gas, is therefore the sum of the kinetic energies of the particles in the gas. So kinetic energy means the energy of the particles because of its motion. Kinetic energy, Chalaka Shakti, the energy because of its motion. So that is internal energy. So all the gases, they have this molecular motions, and because of this, there exists a total energy content due to the motion of this, or the kinetic energy we call it. So the system's internal energy and temperature, if we think about this, the temperature of gas is proportional to the average kinetic energy of its atom. So R is the gas constant, temperature here. And the average kinetic energy is what we call the internal energy. Okay. The internal energy of an ideal gas is therefore the sum of the kinetic energies of the particles. Energy due to the molecular motion. Okay. So that's the point. So energy, because of the molecular motion, we call it internal energy. The molecular motions, the energy also has a connectivity with temperature. Higher temperature, higher internal energies. Okay. Even the flow work, this PV, added into the internal energy later on. That's why U plus PV becomes the total thermal energy there. Okay. Interesting. Internal energy. So this is water and steam. Let's say at gas and liquid phases, lesser, but there is internal energy significant. So saturated water and steam, you can see the UG and UF. Let's see. UG is 2403 here. I'm circling. UF is very small. Same temperature, saturated water and steam. See, that's how the internal energy differences. When it comes to gases, molecules are quite violent. That's why steam can hurt. Okay. So when we are dealing with steam, there should be safety precautions and safety procedures we have to follow. Okay. So steam is sometimes deadly because the higher level of internal energy packed in it. In type of definition, it's okay. Internal energies. So even here you can see this slide. Internal energies 2506 for gas. F means for liquid phase, only 417. Both at 99.6 degrees Celsius. Okay. So the per kg gas phase, the higher internal energy, much higher. Okay, compared to that of the liquid phase. That's a big difference. The bigger the difference, that substance, example here, water, would be very useful for thermodynamics applications. That's why we have steam turbines. For power generations, we have steam engines. Yes. For power generation and to run the other machines and all. So higher differences in internal energies, in enthalpies of liquid and gas phases. So this is the advantage for power generations. Once turned into vapor form, packed with huge amount of energy. Small mass, more energy. Otherwise, we have to have bigger machines if the energy is less, because we have to have more mass. That's the reason. Good. And now, so today discussion, very useful. So you learn about H and U. And this H and U all are thermodynamics properties. So connect this with your one-time note understanding. And your understanding is with some physical sense. I feel it is very good at this time. I need to focus on some practical examples for the other discussion. Give me a second, Buddha.
Sir, excuse me, sir. Mic is not working, sir.
Sorry, Buddha. Very sorry. Yes. මේකන පුත ඇටෙන්ඩන්ස් දානකොට අර ඔක්කොම ඉන්නේ chat එකේ attendance නේ මම chat එක බැලුවේ නෑ ඒකින්ද. So finally mic is off. So what I want to say is this plane is a huge one. Okay. But the power plant or the engine is very small relatively. Again, you are sending the attendance, Nusran. Crazy, really. I asked you to send the attendance at the end of the class. Okay. Don't send me the attendance anymore until end of the class. Otherwise, I will delete that attendance. Simple. I delete the chat and save it. That's it. Yeah. So, very compact, but extremely powerful. So, you can be inspired with this nature of thermodynamic solutions. So, we will see how the thermodynamic knowledge is being applied in these applications. So here reliability is quite high, extremely reliable. And the reliability is the limit of this development. So day by day, when the reliability improves, we can improve the performance. Mainly those are running at very high temperatures. So the metal, the steel, the material used in these engines, there are limitations. So that is the limit of the performance. So if the materials can withstand better high temperatures, they can improve the performance some more. That's why nowadays turbine engines, aircraft turbine engines are more efficient compared to the older ones, let's say 20 years back, and the new ones more efficient because the material advancements in materials Chaturanga again said, maybe I will let you leave the class if you are sending any more. I'll give you attendance after the end of the class. Okay. Quite crazy, really. Mechatronics. තේරෙන්නේ කියන එක attendance එවන්න එපා කියපුවම දැන් එවන්න එපා. තේරුණානේ? This really disturbs the flow of teaching, you know. So I remove Chaturanga from the class for today. Yeah. So we are going to look into what are the real thermodynamics phenomena associated with this so that we can learn something. This is a schematic. Okay, this is a schematic of these engines. There are different engines, but here is the basics. So there is an air intake. And of course, this is turning. And the first set of blades compress this air. And then this air sends into the combustion chamber or the combustion space for combustion, to make the combustion possible, because air, the fuel addition is here. Let me make it big. Yeah? The initial blades all radially turning, and this turning makes the air sucks in. Sucks in means suction. Okay, and then sucks in with further, see, the conically inwards makes, turning these blades makes this conically inwards blades makes this suction air compress. Okay. After compress, this all open passage leave for combustion, because compressed air, as I mentioned to you, air compression makes that air hot as well. Hot means energized. So බාධාම දේවල්. එතකොට air compress කරුවොත්, gas එකක් compress කරුවොත්, it becomes energized. That is what the work done on the air or gas. And become very high temperature. And when the fuel added to this high temperature air with the proper air and fuel mixture, this ignites auto, like compression ignition in diesel engines. Then, because of the turning effect, this air, now highly energized, we call this gas now, gas, passes through this turbine section. See the turbine here? Again, Kumara Singh. So I ask you not to send the attendance. So I let one leave the room. You also want to go, BST? I asked you not to send the attendance, still I asked you to send it. Because somehow we left. So I have to explain from the beginning again. So you have the suction, you have the compression, okay? Then goes for further energizing, combustion, then power, okay? After that, exhaust. So you can see here, same like the engines, suction, compression. Then the ignition is here, turns into gas because fuel burned with the help of oxygen in the air, compressed air. It turns into gas and then turns this turbine. There, the power, because of the expansion, turns the turbine and then exhaust leaves here. Okay. This is an open flow, suctions in, out, again in, out, in, out, again in, out, and then it's leaving it. So you can see here, to have this thermodynamic processes in this continuous nature is very important for a reliable machine to fly. Okay. And it's an open passage here. No valves, no pistons, but you have the compression process. Then compression process makes the air energized. The temperature sufficient enough for auto ignition of this fuel. And after combustion, more energized. Then same like the steam turbine here, energized gas pass through this turbine section and generates necessary mechanical power and leave the exhaust, and the exhaust can bring some thrust so that this propels. Okay, so look into this. It is very important. Okay, so you can see the compression, the turbine effect. Okay, flow in and out. So what matters is the internal energy and flow works together. Enthalpy is important. Energy levels, if you think of here, I just put H1. Input energy level. Intake. Then after compression, because it is same like the balloon effect. So after combustion, H3. After combustion, entering the turbine, energy level H3. Leaving the turbine, H4. And even after that, H5. Possible. Okay. Then in your enthalpy definitions, thermodynamic energies, okay, enthalpies I think I have discussed it. So for this flow works and internal energy. Flow works, again, out becomes the flow in, and likewise for compression. Compression. It is related to this H2 and compression. Before compression, inlet to compression is 1. So H2 and H2 minus H1. Interesting. Then comes the combustion. Because the flow energy. Combustion, added energy. So H3 has more energy. Energized. Level of increase. Good. Then comes the power. At the turbine. So gas flows. Power. So this delivers power. So H3 minus H4 is the work done. Power means the work done, power out. Work done. Is this. Then the energy loss, because H5 is the exhaust, or even H4 can be same as H5. Let's say, but if there is a propulsion, there is a difference. But anyway, I'm taking here compression, combustion. Suction is something free intake, okay? And there is a suction as well. Okay. So, intake and compression, I can take jointly. Suction and compression. But anyway, compression is here. So likewise, you can think of the change in enthalpies when the working fluid flows through the machine. So that is what we are noticing here, okay? Change in enthalpies. Because you know enthalpy is what? It's the energy, the thermodynamics energy in the fluid. When the working fluid undergoes a series of thermal processes, a series of thermodynamic processes. So combustion, there's a proper name for this. Actually, combustion is heat addition. Okay, at constant pressure, here combustion chamber, no pressure rise, constant pressure heat addition. Combustion means addition of heat into the working fluid. So the working fluid undergoes some thermodynamics process. Because of these processes undergo some changes, thereby this power generation and the creating of thrust to move the plane is possible. This simple, small pace works in marvelous ways. Works in very marvelous ways. So you can explore this. So here the turbine section. And you can see the compression, the combustion also here. Here, suction and compression. So one part is low temperature, suction and compression, relatively low. And combustion, this work done, the turbine section is relatively high temperature. That's why here you can see hot section. The cold section doesn't mean that cold, but of course, in high altitudes, temperature can be minus, even minus 40, minus 60, temperature possible. Okay, I think around minus, I cannot remember, it's around minus 40, below minus 40, easily, temperature. So cold, actually cold. When in the flight, this is very cold. So intake, compression, cold. That is very good because cold means for smaller volume, you can have more mass of air to the compression to raise the temperature to the ignition levels. Interesting. The cold section, hot section. You can see combustion chamber, turbine, exhaust, compression, intake. So intake here is the low pressure compression. Low pressure compression and the high pressure compression. Here you can see the blades, the smaller ones with the conical shape. So two-stage compression. Interesting. So you are learning something very important. So we are learning about the compression as well. Now I will show you the 4 strokes, not to say strokes, but in the engine's 4-stroke, you can see the suction here, compression, combustion, power, exhaust. Engine also you are seeing the same. Suction, compression, combustion, power, exhaust. So the combustion means the energy addition, heat addition. That is after compression, because now the fuel is ready to ignite. So power means the expansion of this hot gas. Okay, power. Here. Then the air goes out, so there is a certain energy in and change of the energy levels and finally energy out. So this all happens in the sky, you know. So hot air out and take the fresh air in. So hot air out means you are adding heat to the atmosphere. When this is in flying, even in on the ground, it's the same surrounding. So take surrounding air and exhaust also to the surrounding. So you are adding heat one way. That's how this cycle completes. Okay, that's how this cycle completes. So you should pay some good attention and interest onto this and have some, okay, have some understanding on this, the creations done by technologists. Okay, the same, I separate the compression, I separate the turbine. This is the combustion. You can see the combustion makes some energy into air, and then finally the combusted gas turns the turbine. Okay, so takes air from ambient and return gas to the ambient. It's happened. So that's how you can see somehow there is a cycling of this working fluid. Somehow first air goes in, finally gas comes out. Gas means, of course, it's after combustion when air and fuel together ignites. So don't worry about this, but later we will talk about the energy balances because it is very important. Energy, there is no creation, neither creation, also no losing. So the energy is balanced somewhere. It is same like the wealth in a country. So it is there. Okay, it is there unless it is not sending out. Okay, so there is an energy balance, same like the account balancing and all. So you have in and out and all the things. So combustion of fuel is the way the thermal energy in, and they leave the exhaust to the surrounding. Hot gas, of course, lit hotter, and this release some energy. So the difference is what? The net. Turbine work, yeah, is what? The dumpling, okay? The total. So work done against the energy in, we call this is an efficiency. Don't worry about this at the moment. Okay, don't worry about that. Take this. And here, it's the same energy in. See? Combustion makes the energy. Combustion. Nice. Sorry. This is where the energy comes to run this and make the aircraft fly. Then the loss. Actually, this is Q loss, energy loss. Q means energy. So there is a Q loss. Q loss. When this exhaust, with this exhaust, Q loss. Interesting. Okay. So then you can have your energy balance. Q in minus Q loss. Let's say this is W. It's the total work. Later you can understand this much better. So you can see. So efficient means how effective your energy, the combustion, because of the fuel, to produce some work. I just put here W only. Okay. The W net, actually the W net means this turbines turns the compression. Yes, turning this compressor component is important, but it is to make compression, because that compression work absorbs to the machine itself. And that is not the work out from the machine or the system. That's why we put here net means the turbine work minus the compression work. So that is what the work out. That's why we put W net here. Later we will learn about this. Okay. When I can put W net should be okay. But here I leave W. Okay. So that's how you can see the compression, suction, compression, power and exhaust. Power takes place here at the turbine. suction, compression, power, exhaust. Interesting. Okay. So network means W expansion or W turbine. Let me put here turbine. Minus W compression. So that is the network to run the machines and all. Okay, because internal the air conditioners, whatever the to support the internal energy requirements. Other than that, for the propulsion, the exhaust helps. So the fan means the suction. Then somehow compression. Then you have ignition. Then you have power turbine. Then two turbines, high pressure and low pressure, low torque. Then there is a nozzle as well. Okay. Nozzle. So this makes additional thrust for this. In the space, especially in the aircraft turbine engines, the nozzles are there at the end. So the power generation is to run the internal energy requirements to provide, and the balance, of course, from the part running the fan brings propulsion, and nozzle also brings the propulsion. So together, the fan and the nozzle effect makes the engine move forward. Not the engine, but makes the airplane move forward. Of course, engine makes it. Actually, engine is moving and the aircraft, everything because of this engine moving. Thrust on the engine from this fan and this propulsion. That's why we call anyway, we call this turboprop engines. The propulsion is there. The turbine, somehow the nozzle component is there to have the thrust. Very important. Extra part. So nozzles, you can find about nozzle in your one-time note, nozzles and diffusers. So I just put here nozzle because you will be learning about the nozzles as well. thermodynamics components. Okay, it's quite interesting. So these are very helpful for you. See the nozzle component after the turbine. So this is not simple exhaust, but this makes, because when the gas exits, try to replace the gas, try to replace the surrounding with the gas. As a result, this moves forward. Okay. Third law, every action has a reaction. So that's how this propels, but all the same, okay? All the same. Compression, combustion, power, exhaust. And of course, before compression, there is suction. Same like in four-stroke engines or whatever. You can see this, because working fluid should be sucked in from the surrounding. So thermodynamic principles wise, it is very nice to make aware of this, that thermodynamics makes all. So you have to learn further about compression. Okay. And expansion. No matter turbines. Okay. So no matter engines, compression and expansion. Have to learn combustion. You will be learning. And you will be learning about the nozzles and also diffusers. So open systems. Open means we call the steady flow systems, because aircraft turbine engine is a steady flow system. That's an in and out, this flow is steady. Steady flow system. Okay, you are going to learn. And there are steady flow energy equations. You will be learning this. You can see all now. Where is steady flow energy equation? So how to apply this for this? Fans, compressors, combustions, turbines, and to nozzles, and also to diffusers. You can learn. Okay. Sometimes there are diffusers as well. It's very interesting. Okay, good. So these are the enrichment lessons, daily notes. So connect this with your one-time note I provided for you. And make sure you know everything. Okay.
So excuse me, sir.
Avita.
So, so how will work the lubrication system around this?
Sorry, Buddha. Here lubrication not possible. That's why it's all with the surface finishes should be. Because at over 700 degrees Celsius, no liquid remains as liquid. So the lubrication effect is there with the surface finishes. But the engines running at low temperatures, the 4-stroke and all, your bicycle and car engines, so you can have lubrication. But here the surface finishes. That's why this needs advanced technologies. Not to say advanced technologies, but the different solution approaches. Even you should be able to outline the turbines. Did you get the answer, Guta? Hello?
Yes, sir. That's all.
Okay, good. Yeah, so you can imagine that one more I have to add today for the awareness. Even this solutions are there for power generation as well. The gas turbines. I just put a photo only for your awareness. Gas turbine power generation. There are a lot of applications. Even Noracholi should be a gas turbine. And there may be steam turbines as well. So let me put there are massive for power generations. For hundreds of megawatts, those are more powerful than the aircraft turbine engines. So give me a second, Buddha. So the important thing is with this awareness, okay, with this awareness, you will be able to connect your thermodynamics knowledge for real aspects. That's one. Now you know what thermodynamics means. And thermodynamics goes hand in hand with heat transfer. So the subject normally we call thermodynamics and heat transfer. So all important. Because if we don't go with applications, we cannot understand the phenomena. So our this Yugadanavi power plant is something like this. Yugadanavi, this sold to New Fortress. You have the oil storage and the combustion chamber. There is a turbine running. Same like air intake here, compressor comes, then came to the ignition temperatures, the fuel comes, burned, and turbine, same like the balloon unit turbine, in and out, and the exhaust, connect to generator, and then for the transformers and connect to the grids. So that's one. So you can see if you explore in the web, internet, you can see even the natural gas also, it's possible to know. So this knowledge, now you can see compression, compressor makes compression, combustion, turbine is power, and exhaust. You can see all the 4 strokes, fuel tank also here. All simple, but these are very important because think what's taken place here. Not the pieces here, but the working fluid, the air. What makes change and all. So you can outline the solutions. You can understand what's taken place. Okay. Because with this knowledge, we can analyze thermodynamic systems. First, we should understand what are the What's the sense of thermodynamics for you? Then you can improve the systems. You can look for new solutions. And actually, why not we cannot produce turbines? We can. We can develop. Not for the high-tech ones, but of course, this producing a turbine should not be that difficult, but you may have different levels of the temperature limits, upper limits to operate, but you can have turbine solutions,
Using that.
your own ones. Yeah, Buddha?
So in this process, how will ignite the natural gas?
Yes, because compression makes the air temperature high enough to auto-ignite. Okay?
It's been hot air, no?
Yes, hot air. Compression makes the air hot. So that's why the compression is
So like a the diesel
diesel
engine.
engine, like a diesel engine. So
Yeah.
one way it brings a sufficient amount of air, and the other way that air is compressed so that temperature of the air is high enough for auto ignition, same like the diesel. But the startup, you need ignition. After that, it's natural. Okay, so you have to turn this externally. You have to initiate the turning the startup. After startups, it is auto. So for startup, even for the aircraft engines, after starting it, it's auto. But starting, it needs external power. See, the connectivity of applications, it is very important. Without this, we cannot talk about thermodynamics. No, this will be helpful. The 4 strokes you can see everywhere. Air intake is suction, then compression, combustion, power, and exhaust. Combustion is not considered a stroke because combustion is instantaneous. Okay, instantaneous.
Sure.
Others, there are flowing. Yeah, but anything?
So why we not use the natural gas for the vehicles like that?
Vehicles, of course, there are natural gas usages earlier, but now we are not using. One thing is maybe not sufficient supply and the technology is not established well. But I think in Dubai, Emirates and all, there are natural gas driven vehicles a lot. Just replacing petrol tank with the gas tank.
It's more efficient, you know, sir. Yeah.
Of course. Efficient, and also it's light, maybe. Light, and even the designs, there may be some customized designs, engine designs and more. It depends on this business aspect. Sometimes the oil, they won't promote natural gas, but natural gas is a better solution. There are natural gas driven vehicles overseas. Both options are there, gas or oil, because the same principle. But normally for the oil driven engines, if you put natural gas, your power may be less, because it's designed for oil to give the maximum power. Because oil, the density, energy density wise, oil is more. I mean, the smaller volumes, you can have more energies, but natural gas, maybe you need more volumes. The reason is the density issue. Any more questions? See, now you can ask the questions as well. You may have questions and you may have answers with no questions. Good. So, point is, we are going to learn about this. your one-time note, but you have not seen any of what we have discussed here. And so many things, even in the refrigeration, cooling technologies. Later I will share with you. I need at least 4 hours to discuss cooling technologies, the thermodynamics and some analysis. The most popular one we call vapor compression. Okay. Vapor compression refrigeration. See, the compression term is there. So the nature's phenomena, we are adapting in so smart a way that we can get many things done for the humans' benefits. Okay. So vapor compression, another similar system. So we will study this very well. I can explain all very nicely for you to have a very natural understanding of the subject. That is very important because you cannot have this subject limited to words, not possible. Words are secondary. So that's why I am trying to give this awareness for you. So we are connecting the reality with some so-called textbook theories. So afterward, we will be ready to discuss the thermodynamics laws and all. You feel it extremely simple. Thermodynamics to make you understand, no big deal. Everywhere you see the nature's phenomena. But the very important thing is you should understand the value of this. Okay. Vapor compressions, and also we have to talk about the heat exchangers as well. So all will be connected later with your textbook, one-time knowledge. Okay. So I believe this happened to be the best thermodynamics class taken place in Sri Lanka. You won't believe that. But you explore and you can see all the other lectures, even in Morotu and all, the textbooks knowledge. That's all because lecturers has no much exposure in industries. So then they will learn the textbooks, they teach the textbooks, you learn the textbooks, you pass the exams, you go to the industry, you know only the words and you cannot realize the subject. This subject you have to see through your mind. Okay. Only mind sees this. The engine you are seeing in your car is not thermodynamics knowledge, but what's taken place in the engine, the behavior of the working fluid, how it's taken place. That is thermodynamics. Those who knows that part, the essence, they can develop the engines. The others can develop, but those may not be really engines. So just see the engine as the engine block. You are holding the tail of the knowledge, not the head of the knowledge. Okay. Don't catch the tail, it is nothing. Okay. Have to take the complete one. So that only can be seen through your mind. Okay. So you have to have better imagination, practical sense. And the nature's behavior, what you can see only through imaginations. Those are very, very important. Turbine heat controlling. Turbine heat controlling is the very important is the suction flow rates and the control of the suction flow rate as well as the fuel types. That is very important. Example, the turbine engine, you cannot run with petrol. If you run with petrol, it will be overheated because petrol has higher energy content. So turbine engines are normally run by the kerosene kerosene means it is maybe something like pentane or butane, maybe. Kerosene maybe like, sorry, below pentane. Butane is more higher, right? So butane is gas. Pentane is petrol. Below petrol, maybe the heptane, maybe. I have to check it. So it is in liquid form. So low calorific values, relatively low. Okay. So that's how for the, if you are using the LP gas for the power generations in the power plants, then it's a different engine somehow. Maybe the low power you can design in that way. Controlling heat is the challenge, really challenge for the turbines. That's a limitation. Now you can send the attendance. Okay. The rest, I would say. Any more questions?
Excuse me, sir.
Yeah, Putta.
Sir, burn oil systems are same theory,
Oil
the
systems.
generation, power plant generation.
Oh, Putta, same theory. You can have
Okay.
turbines too. You can have turbines or engines. Same suction, compression, power exhaust. You can have
Okay.
IC engines or turbines. Only power generation turbine system with a pigment. A simple one.
So what about the ratio procedures you want?
Sorry,
Petrol
Putta,
and
give me a second. See, now you can ask the question soon. Within gas turbine power plant, very small. Very small, but this produce something big. Where is the exhaust? Is this gas turbine? No. Let me take it out. Yeah, this one. Then one is the turbine, methane exhaust, suction, compression, combustion, fuel lines. Then the turbine, after that exhaust. So here we no need the thrust. That's why aircraft engines, turbines, it needs a thrust. So only partial work done. A smaller turbine. But here turbine effect is to the fullest and you are sending just the exhaust out. Here maybe all the other controls and all. So that's how it is. Interesting. So turbine engines. So those on the ground can be heavier, bulkier, bigger. No issues. And let me share this screen, maybe power generation turbines. Gas turbines. Maybe I will just put the images, maybe. You can see the very big ones here. See big ones. See gas turbines, General Electric. So massive ones. But let me take this. Okay. How you are seeing the simplicity of this? How you are seeing the simplicity? To have a knowledge of this. Okay. To have a knowledge of this, you must have some elemental level approach, elements. Example, here you can see all blades. So if you think of a blade design, to understand the turbine blades, see, you only need to know about this, the fixation and all. This will be the 90% of the knowledge here. That's right. You to learn 100%, you no need to know about everything. Just 90% is here. Okay. Elemental level. Here there are blades. So all the design phenomena is all common. That's why you should have no fear. So when you are going to see this, don't see this as a bulky one, you know. You have to have elemental level. Understanding. That's why I'm telling you, you can design turbines. Elemental level understanding. See? Even in our childhoods, we have toys, maybe a bamboo, it's like this, but of course, they have some experience-based knowledge, true. But they also try from the beginning, you know, if we have some national level projects of developing this, no big deals, you know. Of course, mega constructions involve a lot of technology and engineering aspects. This needs resources and money. So the governments, earlier they have some good projects and all, but governments, if they can think on this, it's very easy. So your side, see always the essence of the technology. The essence, it is very small. When you further look into this, further simplify. If you further look into this, fan blade. So if you take the blade, analyze it, you know the effect of that. So elemental level understanding and analysis is very important. Then you have no fear of, no matter how big, complicated to advance, you can know it overall. If you have enough guts and the mindset, a very good mindset, you can go ahead. It is very important. Okay. If you need to know thermodynamics, you should know how to apply those. Finally, they should be visible. You have to develop, you have to make, you have to provide solutions. That's why you have to go more than the textbook's knowledge. That is very important. So there are so many things to share with you. So next week, hopefully Friday, we will see you all. And also there are thermodynamics, some videos I put for B2 students. Because B2 Saturday 2 hours, generally I do not miss that session. because I have no much engagements on exams and all these days in Saturday afternoon. So most of the time, the Saturday one, I share the one-time note and the videos, even I can send it to you, but little different from this because even I am teaching real-time, you know. Basically, we have the plan what to share, but sharing is real time. That is better, you know. It's a way how well we are connected. No matter you are on the Zoom very far, but we have some connectivity, you know. That is very important. So you can look into those videos as well. Even I can send you the notes. Even you can get the notes from them and have a very solid, a true knowledge with some solid imaginations. Very important. And this subject is very important for the economies, countries' economies, energy sector, power sector, transportation, even environmental, global warming, everything. You cannot do anything without having thermodynamics knowledge. So Sri Lanka's one of the issue is no one knows thermodynamics up to sufficient level, especially those are sitting on top. Academics, including academics. So that's the issue. So boilers we are importing. Maybe we have fear to do the constructions. Even turbine, we should be able to do one. I think those who are dealing with metals, if someone is, I feel that it's not a big deal. Up to certain levels, with some safe limits, still you can manage. Maybe you can use alternative fuels, biofuels to run this. Efficiency may not be that matter. Yeah. That's why. So have to have some very good imaginatives and initiatives while having this. Okay. Also, we will go for analysis afterward once we know this. Book knowledge, your one-time note, you can see a lot of equations, but you never understand thermodynamics. You can answer questions, you can do calculations, but you have no knowledge. So we have to bring the textbook knowledge to the reality. So that's why the daily discussions very important for. When I feed this to you, you are thinking better than your lecturer. You have better ideas. Okay, that's why you can get this thermodynamics into your fingertips. එක අල්ලට මේ දැනුම ගන්න පුළුවන් පුතා. තේරුණාද? පොත් මාගල් වගේ තියාගෙන නටන්න දෙයක් because nature is quite simple. So try to understand what nature is giving us. Very important. But it's not in the textbooks because that's the way it is. Yeah. Practical පොත්වල තියෙන මොනවද මේ යකඩ කැලි ටික විතර. Essence of thermodynamics is not in practical books. Even not with lecturers. You know. That's the issue. So take the opportunity, get a very good essence of thermodynamic knowledge. Make use of this. Even in your rice cooker, in your kettle, iron, everywhere, engines, turbines, whatever you can see thermal applications, even in LED designs, your microprocessors, the smartphone displays, all everything related to thermodynamics. The computer display using silica, pure silica. So they apply. They are undergoing thermal processes and make it possible to have this LED displays. Okay, thermal processes. That is the first thing, followed by other thermochemical processes. Thermodynamics, nothing much. Okay. Okay. So explore these things. Very important. Okay. Very important, and give some reality for this subject. Only you all can give this. Okay. Very important. So if you cannot understand what I say, look into the records, discuss with your students, your classmates, your friends, and it is your responsibility to gain a very reasonable, practical, tangible knowledge. Okay? That is very important. Good. Later, we will learn some more. And we have enough time, don't worry. Not today. Okay, we have enough sessions to go. So we will learn not only this insight to thermodynamics, but also we will go into analysis in very meaningful ways. Okay, good. And thermodynamics is not maths. I think you have already realized it. Okay, thermodynamics is not maths. It's a wonderful subject, having a lot of secrets unknown to all of us. So be ready to unfold this. That is what thermodynamics. Okay, it's not maths means your maths competency, good or bad, doesn't matter. Okay, you can get the relevant math skills as well, the relevant ones, but thermodynamics is different, completely different. The knowledge secrets. You can send attendance. Then attendance, that is all right. Saving. So it's wonderful. So please go through the video I'm uploading, because you cannot see this. There may be other videos in the web you can go through, because you have the resources. Internet is a huge resource. You have the books and all. But even I believe my lesson also would be very useful. Real-time attending matter. It is very important, not only for the attendance, because you are listening to it, you know. Listening to it. It is very nice. One way it is very sweet, you know. That's why. So, attending the lecture would be, I'm saving your attendance. It's very important. It is not the attendance actually. Attendance is important, that's true. But send it after the class. Maybe I think it's a useful chat or question and I'm opening. So it's attendance that disturbs. So I happen to remove one student also, because that really disturbed. So it obstructs the flow of knowledge that you are receiving. I can't. So wonderful, Putal. Learn this. No matter I teach or not, you have to learn this subject. One of the terribly important subject. The thermal engineering. Thermal engineers are, and the thermal technologists are expensive products, you know. If you can become a very good thermal solution provider, you will be an asset and you will be very expensive. Expensive means your salaries are damn high. Okay. You have jobs everywhere. Wherever you go, in 1-2 months, you can pick up the subject and you can perform. So you have to have that nature of background, basics, and a knowledge that's so useful. Otherwise, in the certificate, you pass thermodynamics. But if you don't know thermodynamics, it's a shame for the university also. Shame for you as well. Even in civil engineering, structural and all thermal aspects you have to consider. Even in energy technologies, thermal engineering is there. So that's the field thermodynamics means. It's the thermodynamics and heat transfer together. Think big, okay? Imagine big. And all simple, there is nothing big. Explore it. Yeah. Have a very positive mindset learning this valuable subject. Very important. That's why I'm trying my best to give the maximum out of this semester. That is very important. Okay. So you should feel good and happy about learning something effective as a subject, thermodynamics. Attendance of everyone. So now you can ask questions as well. Excellent. The best turbine, the best engine, the best power solutions, thermal based, not yet found. Because nature, I don't believe nature gave all the secrets bound by now. Not at all. Okay. So you may be the one finding the best power solutions, energy solutions. You may be the one. Refrigeration solutions and all. Because nature is different. Okay. Receive some very innovative, creative knowledge from nature. You have to be ready for that. And you will be the one providing the best engine, best turbine. No matter big or small, it's the same. So you have to be ready for those who think big. That is possible. That's why there is now no thing as big. Okay, Butala. So let me stop the class there. So hopefully, willing to see you next Friday as well. And I will share this note afterward. I will save this as a PDF. Let me save now. PDF. And I will send this to you right now. And also I will upload this. This is your PDF. So go through this. Very interesting what we have discussed. So nice. Finally, we came to very important knowledge receiving. So learn about this. Later we will go for more analytical aspects. And I'm going to email you this immediately after the session. So that's all for today, Putana. Thanks for joining all. So wish you good luck, and also these days somehow COVID is increasing, so be safe. That is very important. And once the university is open, we can meet and We can do some practicals as well. Till then, even our sessions are something like practical, quite imaginative, and it is good. Blend with some theoretical aspects. So learn this, go through the videos. Don't think that one time listening, understand all, no such thing. And one time note, you also understand. Daily notes, you go through. Video, of course, it is 4 hours from too long, but going through it probably useful. Maybe later we will try to split this into 1 hour sessions, maybe a 30-minute session. So the useful video clips we will make afterward if you have enough time. So take care, all of you, Butala. Thanks for joining the session today. And joining the session is very important for your attendance as well. Okay. But keep the disciplines when you are sending the attendance, and you should have no worries. Because you have time for the attendance. Okay then. So let me stop the class. I think last attendance I say. Okay. Thanks, Putala. Then I'm going to stop the class. See you next week. Bye then. Bye.
Thank you, sir.
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 Thank you, Putala. Take care. Bye.